Here is the next one, or arithmetic and geometric sequences 2. So we're going to focus more on geometric in this one, whereas the other one was more on arithmetic. Okay. So looking at these, the first two are just deciding if it's arithmetic, geometric, or neither. Remember, arithmetic grow with addition or subtraction of the same number, geometric multiplication or division of the same number, and neither is some other pattern. So first thing to do is to look to see if you can do it arithmetically. What is that constant difference? Okay, so is there a constant difference, the number that you're adding by? Negative 22 to 20, we would add 2. Will that get us to negative 18? Yep. To negative 16? Yep. So it does have a common difference, which means it's arithmetic. So to finish it out, negative 12, negative 10, and negative 8. For number 2, start off that same way. Negative 4 to 20, you'd have to add 24. Can you add 24 to get to negative 100? Nope. So let's try multiplication. Negative 4 to get to 20, you'd have to times by negative 5. Negative 5 times 20, does that give you negative 100? Times by negative 5, does that give you positive 500? Yeah, so it's got a common ratio. And we're timesing by a negative 5. So it would be geometric. Now to find the next three terms, we would just take that the next number, negative 2500, times it by 5. And we'd get a positive 12,500 times that by 5. By negative 5. And we get negative 62,500 times that by negative 5. And we get 312,500. Okay? So there we go. Now, we want to find our recursive formulas. Remember, recursive formulas, if we look at a table, okay, and so we've got that sequence. So our first term is 2, our second term negative 10, our third term 50, our fourth term negative 250. Okay, so this left side is which term we're talking about. Okay, the right side is our output. Okay, our numbers. Now, recursive connects these output numbers, okay, using the common ratio, which from 2 to negative 10, negative 10 to 5, we'd be timesing by a negative 5. Okay, so my common ratio is times by negative 5. So to find the next term, recursive is all about finding the next term. To find the fifth term, which would be the next, we go back to the fourth term and we times it by negative 5. Okay, which gives us our next number. Okay, the way we write that, there's two different ways. We go a sub n, which stands for our next term. Okay, to get the previous term, right, that would be like a sub 5 is what we're looking for. Well, we would need the fourth term, so we would need a sub 4, and then we'd need to times it by negative 5. Okay, well, to find this one, okay, we just look back. Now, these numbers, 4 and 5 here, these are our subscripts. They just stand for the term, which term it is. They're not referring to the number 4 or the number 5, but the fourth term, which is negative 250, and the fifth term, which is what we'd find out. So instead of a sub 4, that's not 4 times negative 5. A sub 4 is a stand-in for negative 250. Okay, so we'd multiply it like that, which would give us a positive 1250. Okay, so when we're writing the equation, right, the equation is we're asking for the nth term. The nth term is any one of these terms. It's the term we don't know, okay? So it's a variable. Well, just like here, to get a to the fifth, we ended up needing a to the fourth. Well, what is 4? Isn't that the 5 minus 1? So 5 minus 1 would get us 4. So we take the previous term, which we write as n minus 1, a sub n minus 1. Still reminding ourselves that this is an output number. Okay, so it's that number here, and then n minus 1 would be the previous number. So this one is referring to an output as well, but the previous output. Okay, because when we were looking at 5, we went 5 minus 1, or 4, which was the previous term. Okay, so when we write our equations for recursive, we always go a sub n equals a sub n minus 1, and then what pattern did we apply? We times by a negative 5, reminding ourselves that these are both outputs. Okay. Now another way we like to write it is using function notation. We call it f of x and f of x minus 1. It's still the same concept. It's an output and an output. The previous output, which we times by negative 5, will give us the next output. That's what this all stands in for. Okay? So, there's one more thing we need to make our equation complete. Okay? Just like in order to get the next, we need the previous. Well, when we first start out, how do we know where to get this number? Well, we need a starting point. Okay? We need a starting point. So we can go a sub 1, because that means that's our first term, and that was 2. Or we can go, I guess, let's write it this way. We need to know where to start our pattern. So we start at 2. Or for this one, we'd write f of 1 would equal 2. That means the first term is 2. Or a sub 1 would equal 2. Okay? Now, when we get past recursive equations and we get to explicit equations, we were actually going to need more than the first term. Okay? We're going to want to go to the 0 term. We go to the 0 term by going backwards. So negative 2 over 5 would be the 0 term. That's what we truly call our start number. Okay, that's truly what it is. So this one I probably shouldn't have called it the start. I should have called it first term. Okay, so you can use the a sub 1 on all of these, but a better way to do it is to just get in the habit of always going back to the 0 term. Okay, and so then I'd go a sub 0 equals negative 2 over 5. F of 0 equals negative 2 over 5. My start number is actually the 0 term, negative 2/5. Alright? So that's the idea behind the recursive and why we use these formats. Okay? Now, these look very similar, but they're different. This one we use more when we're dealing with functions, which we'll get into. This one is strictly for sequences. Okay? Alright, let's bust these out now. So, my idea would be to just kind of make it a table here. Actually, probably like this, and go, well, this is my first term, second, third, fourth term. If I want to go back to the 0 term, I'll need to figure out what that is. So how is this growing? 4 times to 12, then to 36. Hopefully we see we're times them by 3. So my common ratio is multiplying by 3. So if I'm going backwards, I would divide by 3, and I'd get 4 divided by 3 for my 0 term. So for my equation, I go a sub 0 equals 4/3. Or I could go a sub 1 equals 4. Both of them work. Then I would go a sub n equals a sub n minus 1. So the next term is equal to the previous term. And what's my pattern? Timesing by 3. Now, just to show you something, whenever I am writing a recursive equation, it is always going to look like this. Those purple parts are always going to be the same. Now, you only need one of those. Okay, so we'll just eliminate this one for now. So you'll always have this purple part, you'll always have this purple part. The only time you won't is if you decide to, say for example in this one, write it like this. Okay, and then our common ratio, negative 1 to 5, 5 to negative 25, timesing by negative 5. So if I made this into a table, first, second, third, fourth term, so my 0 term, we'd go backwards, would be a positive 1 over 5. So I start at 1/5, my pattern, timesing by negative 5. Okay, see the similarities? This and this stay, that's the same thing. This and this are the same thing. They all mean outputs. They're dealing with these numbers, not with the inputs. Okay, so there was number 5 as well. And that's really all it comes down to. For now, we can just use the a. You could have also went f of 1 equals negative 1. That would have worked too. So a sub 0 equals a sub n equals a sub n minus 1. And I can just go through and write these in first if I really wanted to, because this is the stuff that we do for every single recursive equation. Okay, now I just need to find the rate and where it starts, and we're good to go. So turn it into a table. That's my first term, second term, third term, fourth term. 4 to 8, 8 to 16, we're times them by 2, negative to positive, times them by negative 2. So my rate times by negative 2. Rate times by negative 2. Okay, if I go back to the 0 term, dividing by negative 2 would be a positive 2. So a sub 0 equals 2. Okay, number 7, same idea. 4 to 8 to 16, times them by 2, right? So ratio is timesing by 2. That's what I put in for my growth. And then if I went back, it would go back to 2 for my 0 term. So a sub 0 equals 2. Okay, number 8. Got my first, second, third, and fourth term. If I'm going back to my 0 term, 1 to 4, 4 to 16, I'm timesing by 4. Positive to negative means it's negative 4. So timesing by a negative 4. Going backwards would be negative 1/4, because negative 1/4 times negative 4 equals 1. Alright? Good enough, right? Okay. Now, let me pull out something else that I want to do. Oh, we got 2 more. Take that back. So, a sub 0 equals a sub n equals a sub n minus 1, or f of 0 equals and f of x equals f of x minus 1. Okay, so what's my ratio? So my first term, second term, third term, fourth term, I want to go back to the 0 term. 1 to 6, 6 to 36, we're timesing by 6. Ratios timesing by 6. Going backwards would be negative 1/6. So where did we start? Negative 1/6. How's it growing? Timesing by 6. Okay, number 10. Same idea. Make it into a table. 0 first, second, third, and fourth terms. 3 to 15, 15 to 75, times them by 5. So it would be negative 3/5 for our starting number. And we'd be timesing by 5 here, because that's our common ratio. Alright, now I want to take one of these, and let's see, I want to take a simpler one. Let's take this, no, this one right here. Okay, I'm going to do something with it to help us understand the explicit formula. Okay. Alright, so looking at this, okay, so see, we started with 2, yeah, or 4 actually. 4 was our first term. Then 8, 16, 32, 64, and 128. Okay, so we found out that our ratio was timesing by 2. Okay, now this is why we want to go back to the 0 term, because if we start with this as our first term, as this is our starting point, that would be 4, right? How does 4 turn into 8? Well, we times it by 2. How does 4 turn into 16? Well, we times it by 2 twice. How does 4 turn into 32? We times it by 2 3 times. So if we wanted to get to 64, 4 times 2 times 2 times 2 times 2, right? Then, because we don't like to write it out this way, and this would be one more. We don't like to write it out this way, we shortcut that, right? So 4 times 2, and how many 2's are there? There's 5, so the shortcut is to the 5th. This one, 4 times 2 to the 4th. 4 times 2 cubed. 4 times 2 squared. 4 times 2 to the 1st. This one technically 4 times 2 to the 0. Now what do you notice about all these powers? 0, 1, 2, 3, 4, 5. They correspond with these number, but they're always one behind. Okay? So if we start with the first term, it's 0. So that would be like 1 minus 1, right? Then second term would be 1, so 2 minus 1. Then 3 minus 1, 4 minus 1, 5 minus 1, and 6 minus 1. So in order to connect this, because that's the whole point of the explicit connects this input with this output, whereas the recursive connected this number with the next one, okay? So in order for it to work, when you're using a variable, you'd have to go y equals 4 times 2 to the x minus 1 for it to work. So because of that, you're much better off to just go back to the 0 term. Because if you go back to the 0 term, you don't need that minus 1. Okay? So going back, see where time that was 2, right? So it would be 2 times 2, 2 times 2 times 2, and this one actually is kind of weird because of the number, right? Okay, but you'd actually end up with 2, then 2 times 2 to the 1st, 2 times 2 squared. Then to get to 16, from 2 to 16 would be 2 times 2 times 2 times 2. So there's 3 of these after the starting. And this was kind of a bad example, wasn't it? Because we're dealing with the same number. So the pattern here now that you can see, so 2 times 2 to the 5th, 2 times 2 to the 6th. This with n would be a sub n would equal 2 times 2 to the nth. And this would be f of x, or y, equals 2 times 2 to the x. But here, these powers, the times you're multiplying by, they match up with these input numbers, so you don't have to do that minus 1. That's why I say always go back to the 0 term. Okay? And just get in the habit of doing that. Okay? So, the interesting thing too is when we wrote the explicit here, okay, so the explicit, this is the recursive, the explicit, okay, would be a sub n equals our starting number 2 times our growth 2 to the x, or the n in this case, because I used n. But notice, do we have our starting number? Yes. Do we have our starting number? Yes. Do we have our growth? Yes. Do we have our growth? Yes. So those two things, the start and how it's growing, okay, they both are in both of those, just in different parts. Okay. Now, if we were to go back and do this with an arithmetic version, okay, so say it was 2, 4, 6, 8, 10, 12. It's the same process, but the difference is you're adding, because the growth is adding, not multiplying, but you end up with a similar pattern going on here. Okay, so whether it's arithmetic or geometric, these are going to be the same process. The difference, arithmetic's going to have a plus. Arithmetic's going to have a plus and a variable down there. Okay, that's the only differences. So if you can do it for geometric, you can do it for arithmetic, and vice versa. All right, let's finish up by looking at these. So we'll get the common ratio, then we'll write the explicit. All right. Okay. So once again, I'd start off by making a table. And then that's my first, second, third, and fourth term. I want to go back to the 0 term. So what's my ratio? So looking back at this ratio, 3 to negative 9 to 27 to negative 8, we're timesing by negative 3. So that's our times by negative 3. Okay. So going backwards, dividing by negative 3 would bring us to negative 1. So there's our start number. Over here, that was a sub 0. For the explicit, that's the first number. So I just go y equals negative 3 times, oh crap, negative 1. I'm totally screwing you guys up now. Negative 1 times negative 3, and then to the n. Okay. Suppose we should keep it a sub n, since we're dealing with these. Okay. Could you write it y equals negative 1 times negative 3 to the x? Yes. Could you write it f of x equals negative 1 times negative 3 to the x? Yes. I accept any one of those. They're all the same to me. Are they slightly different? Yes, they're slightly different. But for us, it's not as big of a deal. Okay? So 12, same thing. Okay, go back to the 0 term. So 4 to 16 to 64, we're timesing by 4 each time. So going backwards would be a negative 1 again. So I'd go a sub n equals my starting number, negative 1 times my growth to the n. If I was for some reason doing explicit as well, just to remind us, it'd be a sub 0 equals negative 1, then a sub n equals a sub n minus 1 times 4. Okay, remembering these are outputs. Okay, the only input here I see is this one right here because it's not connected to any variable. Alright, 13. First term, second, third, and fourth term. Go back to the 0 term, 4 to 24 to 144. Looks like we're timesing by 6. That's our common ratio. So going backwards would be negative 4 divided by 6, which we can reduce to negative 2/3. So, as an equation, a sub n equals my starting number, negative 2/3, times that common ratio, 6, and then because it's multiplying by 6 every single time, we take it to the n. Okay, number 14. So you can see it's the same process. You first start out by finding the ratio, take it back to the 0 term, then write your thing. So 2 to 8 to 32 looks like we're timesing by negative 4. So I could go y equals instead of a sub n. Y equals, taking it back, negative 2 divided by negative 4 would be positive 1/2. 1/2 times negative 4 to the x. Okay, 15. Make my table. First term, second term, third term, fourth term. Go back to the 0 term. 4 to 20, 20 to 100. Definitely timesing by 5. So taking it back would be negative 4 divided by 5, or negative 4/5. So I'd go f of x equals my starting number, negative 4 divided by 5, times my growth to the x. Alright, 3 more to go. Zero, 1, 2, 3, 4. 3 to negative 6 to positive 12 to negative, so I'm timesing by a negative number. That should key us off by now. 3 to 6, 6 to 12. Looks like we're timesing by a negative 2. So a sub n equals, so going backwards, 3 divided by negative 2 would be negative 3/2. Negative 3/2 times negative 2 to to the n. First, second, third, and fourth term, going to my 0 term. 3 to 9 to 27, times them by 3, going backwards. 3 divided by 3 is 1. Okay, so just one more thing to add on this. No, let's not do it on this one. So we'd go f of x equals 1 times 3 to the x. Okay, looking at 18, our last one here. So first term, second term, third term, fourth term. 2 to 8, 8 to 32, times them by 4, that's our growth. Okay, now, remember the recursive is like how we're thinking. So, going back to the 0, 2 divided by 4 would be 1/2. Okay, recursive I'd say my first term, a sub 0, or my 0 term I guess, not really our first, okay, would be 1/2. Then, if I'm going to find my next term, okay, say I wanted to find the fifth term, right? That's what this stands in for, this fifth term here. I would need my fourth term, which is n minus 1, and then times that by 4. So we take 128 and times it by 4. And that works great when we're dealing with small numbers. But what happens, okay, and this is why we need both equations. The recursive models how we think about it, okay, which is what math is supposed to do. It's model how we think, how we experience things. We experience patterns in this way, okay. The problem is what happens when we get, and we want to go, say, clear to the 150th term, okay. In order to get the 150th with the recursive, I would have to go back to the 149th, which means I'd have to keep going back. I'd basically have to be counting by this. Okay, that's not very helpful. It's not quick. It's slow, and we don't like that. So that's why we have the explicit, because the explicit connects this 150 with my number. Okay, so for my explicit, I go y equals my starting number 1/2 times my growth to the x. Because it's not x minus 1, sorry about that, Bell. Because it's not x minus 1, or it's not a sub n, or it's not f of x, okay, because it's the x, it refers to this number. So I could put a 150 in there, and that would get me what that result is, okay. I would go 1/2 times 4 to the 150th, and I end up with an enormously large number, okay. But that's why the explicit is so useful, okay. Now just to remind us, they use the same information. It's just how it's connected to the variable. These are connected to outputs. This is connected to an input, okay. Input here, these represent outputs. Outputs, you need to know the previous one to get the next one, and the pattern, and where to start. Explicit, you just need to know that pattern because it keeps growing, right? We dealt with the pattern, keeps growing, so we can use a shortcut essentially to help us figure it out. And there we go.